Florida's ocean floor is collapsing in ways scientists never expected. In late 2024, NOAA vessels mapping the Florida Straits found massive sinkholes forming in real time, some wider than football fields and deeper than skyscrapers. These aren't stable scars of the past, they're active, expanding voids that could reshape the seafloor. What's driving them? Methane eruptions, brine pockets, or hidden aquifer collapses? And how close are these hazards to shipping lanes and coral reefs? Today, we'll uncover the forces tearing Florida's ocean floor apart and what it means for the coast. Active collapses mapped. When scientists first announced that sudden depressions had been found forming off Florida's coast, the news sounded almost unbelievable. Yet sonar mapping from NOAA expeditions left no room for doubt. Vast, circular pits had appeared on the seafloor, some measuring hundreds of feet across, large enough to swallow entire city blocks if they were on land. These are not the exaggerated giant holes of urban legend or movie plots, but they are no less alarming. They represent active, fast-forming seafloor sinkholes, depressions carved into sediment layers that were thought to be stable. The scale of these collapses is staggering, with depths equivalent to 30-story buildings and diameters rivaling major stadiums. To oceanographers accustomed to slow geologic change, the suddenness of these features is what makes them so unsettling. Sonar images reveal details that deepen the mystery. Inside the sinkholes, swirling sediment plumes spiral upward like underwater smoke, evidence of material collapsing into the voids below. Chemical sensors mounted on underwater drones show abrupt shifts in water chemistry, changes in oxygen levels, pH, and even methane concentrations, all within a few feet of the depression's rims. These signs point to a rapid process of sediment failure, not the slow, rolling dune migration or erosion typically seen on the seabed. In fact, the turbulent flows resemble the behavior of Florida's famous blue holes, deep vertical shafts in limestone that extend far below the seafloor. By comparing the data from these new collapses with older blue hole studies, researchers confirm that they are looking at a very real hazard and not just another natural quirk of the ocean floor. The combination of spiraling sediments and chemical anomalies suggests powerful forces are acting beneath the surface, destabilizing material that should otherwise be locked in place. Equally concerning is where these collapse zones are appearing. Some lie dangerously close to Florida's coral reef tracts, ecosystems already fighting for survival due to bleaching, rising temperatures, and pollution. A sudden slump of sediment or collapse plume could blanket fragile reefs in suffocating clouds of debris, hastening their decline. Others are located near heavily trafficked shipping lanes, places where massive cruise liners, container ships, and fishing vessels pass daily. A large sinkhole opening beneath these routes could stir currents strong enough to disrupt navigation, while exposed edges may pose a threat to anchors and submersibles. Remotely operated vehicles, ROVs, which often investigate these sites, risk being damaged or even pulled into unstable sediments. For marine infrastructure, cables, or pipelines laid along the seafloor, such collapses could prove catastrophic. Scientists emphasize that these are not isolated events. The clustering of sinkholes in certain regions points toward a larger, systemic process at work. Some pits even appear aligned along invisible lines, as though connected by hidden pathways or underground tunnels within the seafloor. That possibility raises urgent questions. If these collapses are linked by subterranean channels, then one failure could trigger another, creating a chain reaction across the continental shelf. What might look like a single depression today could actually be the surface expression of a much bigger and more dangerous plumbing system beneath Florida's ocean floor. The pattern hints at underground plumbing, channels, and cavities linking one collapse to another. So what exactly is tunneling beneath Florida's seabed? Hidden plumbing, real triggers. Florida's geology has always made it vulnerable to collapse. On land, the state is famous for sinkholes that suddenly swallow homes, parking lots, and even entire streets. The culprit is karst, porous limestone that dissolves over time as slightly acidic groundwater seeps through it, carving out hidden cavities. Eventually, the roof of these cavities weakens, giving way with little warning. This process has been well documented inland, but researchers are increasingly convinced that the same dynamics are unfolding offshore. The Florida platform extends far beneath the water, made of the same carbonate layers riddled with weak zones. With ocean circulation, salinity fluctuations, and pressure from tides and storms, the conditions for dissolution and collapse may be even more extreme than on land. In other words, the ocean floor near Florida may be subject to the same geological fragility that makes the state notorious for sinkholes on the surface. Evidence suggests that these offshore voids aren't isolated. Instead, they could be connected by vast subterranean channels, natural plumbing systems that snake beneath the seabed. Just as underground rivers link Florida's inland springs and sinkholes, similar conduits may run beneath the continental shelf. If one roof section begins to thin due to chemical erosion or sediment flushing, the stress can transfer to neighboring sections. A localized slump may then cascade downslope, triggering multiple collapses in quick succession. This kind of domino effect explains why clusters of sinkholes appear in specific areas rather than being scattered randomly across the seafloor. It also raises the alarming possibility that one failure could set off a chain reaction, spreading instability across an entire region of the continental margin. Adding to the natural risks are the pressures of modern life. Florida's groundwater has been heavily tapped for agriculture, urban growth, and industry. When aquifers lose water, the pressure balance changes, sometimes leading to void formation or collapse far from the pumping site. On shore, this can cause sudden sinkholes under neighborhoods. Offshore, it could mean unseen changes in pore pressures that travel through aquifer pathways and destabilize sediments beneath the seafloor. Extreme weather conditions aggravate the situation. Storms push strong pressure waves into coastal aquifers, while heavy rain brings on sediment loads, further weighing down already delicate strata. On the other hand, droughts draw water tables down, breaking the fragile equilibrium that prevents cavities from collapsing. By themselves, each of these stresses may not trigger a collapse, but together, they might tilt the system towards failure. Offshore detection of these threats is fraught with difficulty. On land, there are clear indications: cracks in driveways, leaning fence posts, and sudden water losses from swimming pools. The underwater equivalents of these would be subtle, microcracks in sediment layers, gradual irregular tilting of the seabed, or unexplained seepage detected by ROV sensors. Scientists are trying to get ahead of the calamity by making monitoring technologies better at picking up these early warning signals. They are pondering a kind of monitoring that would include using seafloor tilt meters, pore pressure gauges, and chemical probes in concert to catch a collapse before it happens. However, the ocean is too big, and most of Florida's beneath-the-sea plumbing remains invisible. But cavities don't collapse without energy, so what's driving the punch that makes the seafloor give way? Pressure, gas, and lava potholes. If Florida's offshore plumbing system provides the cavities, then pressure is the force that turns them from hidden voids into catastrophic collapses. One of the key culprits is methane hydrate, a strange ice-like compound that traps methane gas molecules inside cages of frozen water. These hydrates remain stable under cold, high-pressure conditions at the seabed. But when ocean temperatures rise or when sediment pressure shifts, the hydrates destabilize, releasing gas into surrounding layers. As methane expands and rises, it can fluidize the sediment above, prying open weak layers and forcing cracks to widen. Imagine the seafloor being lifted from below like a car jack, then suddenly dropping when the gas pocket vents. The collapse is not gradual, it is violent and fast, leaving behind the yawning pits researchers now call oceanic sinkholes. The threat doesn't stop with methane. Brine pockets, highly saline water trapped deep underground, can also exert destabilizing force. When these brines shift, they alter buoyancy and pressure balances within the seabed. Combined with rising gas columns, they create zones where sediment is no longer strong enough to hold itself together. This dynamic mirrors processes scientists have observed elsewhere in the world's oceans, where pressurized fluids suddenly vent, carving craters and channels into the seabed. For Florida, the danger is magnified by the fact that these processes are happening in a region bordered by coral reefs, heavy shipping traffic, and densely populated coastlines. To understand how such pits form, researchers often look to analogues from other parts of the world. One striking example comes from work led by University of Florida geologists on collapsed lava bubbles along the mid-ocean ridge in the Pacific. There, scientists discovered semicircular pits and jagged depressions caused not by erosion, but by vapor trapped beneath lava flows. Because molten rock spread over the ocean floor, seawater that was trapped below vaporized into the bubbles' inflation, which buoyed the lava sheets. Those bubbles, under the extreme pressure, crushed very quickly, leaving hardened potholes behind. Florida's continental margin is not a volcanic one, yet the physics are strikingly similar. Fluids are trapped under a roof, pressure builds, buoyancy lifts the roof, and voila, quick implosion shapes the void. The analogy goes that such pressure and vapor-brine interactions might be responsible for shaping the seafloor of Florida in ways that scientists are just beginning to map. Florida has its sinkholes on land, from that different angle, dominated in three types onshore: solution sinkholes in which limestone slowly dissolves, subsidence sinkholes in which thin soil masses slump into cavities, and collapse sinkholes, the deadliest, which come up suddenly when the ceiling of a cavity collapses. These are also true for offshore, but conditions there are more stringent. Deeper pressures, saline chemistry, and sloped terrain mean that a small void can grow into a major collapse much faster than its counterparts on land. The warning signs, on land, driveway cracks, leaning trees, or sudden water loss, translate into the underwater world as microcracks in sediments, unexplained tilting of seabed structures, or sudden plumes of gas and brine detected by ROVs and seabed gauges. The parallels between land and sea reinforce one troubling truth: the processes reshaping Florida's coast are not exotic, they are extensions of familiar hazards, now playing out beneath the waves with amplified force.